Uh,
Um,
yeah, just
did it?
it depends on the math. If it's math I've done 100 times, not so much. But if it's stuff like calculus or something, yeah, it's
Hmm.
real useful to have some, like 30 minutes to just kind of think about the math that I went over.
Oh, for sure. Yeah, like you need like a brain break, you know?
Yeah, yeah, or
Yeah,
just thinking about the math, even not taking a break.
right.
So what do we got? Did you send me any pictures or?
I did. Did you get it?
No,
Man,
I did not.
I even put in a subject. This I just don't get it. That is just weird.
That is weird.
Because I put in a
I had a little
I
bit of internet problems earlier today that lasted for about 5 minutes, and I couldn't figure out whether it was on my end or the student's end. Uh,
right.
but it's been fine since then.
Huh. Because I sent it even at 7:30 to kind of give it time to
Yeah,
process. But man, I guess you
I'm
didn't get it.
baffled. That's one of life's mysteries until it remains solved. You went and watched everything your mom did?
Yep. I did exactly like.
You have exactly the same phone as you? Do you like both have Apple's?
Yep. We do. We both have iPhones, so I mean, it's like
There's some that can't be right. There's
I
something's
know.
going on.
It must be. I
And
mean,
yet you sent me stuff many times, but it gets here very often, like the next day.
oh, that's weird. Yeah.
Very weird. I guess the only solution is to go have your mom do it again.
Yeah, I'll have her do it. Hey, Mom, can you send the math? It didn't work again. I did like the exact same steps you did. I don't know why it's not sending.
Next time you try, have her watch.
Okay. Yeah.
Maybe figure out what you're doing. You might be doing something real minor that I don't have an iPhone, so it's hard for me to know what it might be.
Right.
But
Yeah.
it's just very strange. You need to get to the bottom of it just to
It
explain the
is.
mystery.
Yeah. Man, because I've done like all the exact same
Do you
steps that she's
do you ever
done.
send pictures to other people's email or do you send it to phones usually?
I send it to phones usually.
Okay.
Like by text message.
When
I
you
could try that.
you sent it to my phone once, and
Uh-huh.
what I got wasn't visible, and it said
Huh.
download. And when I hit
Right.
download, it didn't do anything.
It didn't do
So,
anything.
yeah, and that's happened with a few different people with me. I'm
Yeah.
not sure whether I can even receive it by my phone.
Right.
But I don't want to get it by my phone anyway. I want to get it. In other words, if it's on my phone, I can't bring it up on the screen.
Yeah. Here, I got it. I'll show you. So you take pictures. Sorry, I'm just showing her the steps of what I do to make sure
No,
I'm
that's
doing it
fine.
right.
That's fine.
Yeah, so I take a photo of that. I go to this, upload. Actually, here, go to camera.
No, go to photos.
Well, that's the same thing.
Okay.
Don't do, no, no, no. It's not necessarily the same thing. We're trying to find any little subtlety that makes a difference.
Yeah, David, that one.
Do you have his right email address?
Yeah, David Cowan 1949 at gmail.com.
Yep.
And then here,
You're doing it too fast. Stop.
and then review. I'll just say that for the subject line.
Hi, David.
How are you?
Good. Sorry.
Good.
The dog just ripped Dylan's $200 winter coat.
Oh my goodness.
Actual says.
I'm a little grumpy. Sorry.
He's competing with my dog. My dog went through about $1,000 worth of stuff before
Oh,
Oh my gosh.
finally stopped chewing everything.
jeez.
I mean, cords. I'm
Man.
lucky. I'm lucky she didn't electrocute herself. Okay,
Jeez, now you got it.
I just got it. Oh yeah, you can see, huh?
Yeah, you got
Yeah,
photos.
that's you gotta go to photos then.
Yep.
That's the strangest thing I've ever seen. That's
Okay. Go to photos.
yeah.
That's what I do. Whenever I send a picture,
You got it.
I go to my gallery,
Mm-hmm.
select the photo I want to send, and then share it as a Gmail, with the Gmail account.
Uh-huh. Okay, yeah, I guess gotta do that from now on. Because I usually got a camera and then you click on the like bottom left-hand corner to pull the picture up, and then you hit the upload button to mail,
Mhm.
and then I guess that just doesn't work. That's interesting. Yeah. All right.
Okay, we're going to start on 37.
Yeah.
You just sent one document?
I did, yeah.
Yeah.
Just this review. This is the last page of review that I have to do.
This is odd because this was a calculus problem that I had earlier today also.
Oh, interesting.
Yeah.
Okay.
This
Yeah.
this is the classic calculus problem.
Okay. All right.
And let me show how we're going to do this.
Sure.
We have a rectangular piece of cardboard.
Mm-hmm.
We're going to cut corners out that are squares
Okay.
of all four corners,
Mm-hmm.
same size.
Okay.
And we're going to be left with a place that we can fold up those flaps,
Okay.
creating an open top box.
Okay.
All of these dimensions are X.
Right.
Cardboard is 18 by 13.
Okay.
Now, the question is what should X be to make the largest volume possible?
Okay.
Notice that if X were really, really tiny, we wouldn't have
Uh-huh.
very much height to the box.
No.
Our volume isn't going to be very big.
No.
And if X is really, really big,
Mm-hmm.
then you're going to have like a briefcase. It's very, very thin, and it's not going to have much volume.
Okay.
So the question is, how do you figure out what to make X so that you have the biggest volume possible for that box? And this is a real life problem for manufacturers of boxes. They want to use as little material as possible to build as big a box as possible.
Mm-hmm. Okay.
Okay, so let's talk about the volume.
Okay.
What's volume of a rectangular box going to be equal to? What's the general equation?
Base times height times width.
What's the base in this case?
18.
No, that's the base of the cardboard, but we're looking for this distance. That's going to be the base of our box, right? In other words,
Right.
these, let me, gosh, what happened to my colors? Weird.
Right. Uh-huh.
Weird.
Yeah.
What was I going to say? We're cutting out the yellow areas, and then we're going to fold up everything else. In other words, that folds up, and we end up with a box.
Right.
Okay?
Okay.
So the base is how much? If this is X and this is X, in other words, X is going to be a single number.
Okay.
So what's the base of our box? Our box is this area surrounded by the four dotted lines.
Yeah.
What's the base equal to?
It'd be equal to 9.
Don't guess.
No.
That's
What are you cutting out?
How about 18 minus 2x?
Then it'd be minus. Okay.
See why it's that? In other words, it's 18 from end to end, and I'm subtracting one x there, and I'm subtracting another x there. So it's 18 minus 2x.
Okay.
What's the width?
13 minus 2x.
And what's the height?
The height would be, well, would that be the height? Well, that's the
Tell me what it would be.
13 minus 2x.
Don't say with that, because I can't tell what you're talking about.
Oh, well, the 13 minus 2x would be the height.
Well, that's the width. In other words, that's this distance from here to here is 13 minus 2x. And
Yeah.
the distance from here to here is the base, which is 18 minus 2x.
Uh-huh.
So what's the height? Think of this box. It's going to be a certain height. What's the height going to be? What's the distance from here to here? Isn't that going to be the height? When we fold up those flaps, in other words, everywhere where I have marked red is going to be folded upwards.
Okay.
So the height is what?
So just 2x? It'd be...
Just x.
Is it just...
Yeah.
Okay.
Picture the box.
Yeah.
In other words, everywhere these four corners are missing.
Uh-huh.
And now you have a flat box that you're folding up these flaps, and all four flaps make the four sides of your box.
Okay.
And this distance is x. So that's going to be the thickness of your box.
Okay.
Okay? So there's the formula that we want to optimize. We want to make a maximum volume.
Okay.
Well, if this were a quadratic, it'd be easy. We'd just find the vertex of the quadratic. But this is going to be a cubic. And because I have an x there, an x there, and an x there, at some point I'm going to have x cubed.
Right.
Okay? So let me read their problem. I'm kind of curious as to why you're getting this problem.
Yeah, I am too.
Let me finish reading it.
Yeah.
Okay. Now you're trying to build as big a box as possible. You're storing M&Ms.
Uh-huh.
Okay? So how long should you make the cuts? What is the maximum volume? I can answer all of those questions, but only with calculus. How many M&Ms do you think you'll have if each M&M takes up that much space? Well, I'm going to take my total volume and divide it by that and get the answer. Wow, you are getting into calculus. I'm looking at the next question. Increasing and decreasing, that's all calculus.
Is it really?
Do you know how to do first derivative?
I don't think so. We haven't talked about that, honestly.
Well, this is very curious because there's no pre-calculus way to do this problem. There's only calculus. You have to take the derivative of the function, set it equal to 0, and solve it. And it gives you, oddly enough, not an integer number. The answer is usually like 3.179 or something like that. Okay?
Yeah.
So it's not an obvious answer that you would ever guess. And in fact, by trial and error, you would not be able to come up with the answer.
Wow. Okay.
So the question is why are they asking you this question when you have not had the calculus to solve it?
Yeah, he hasn't taught us the calculus to do this, which is beyond me. I don't know why he would do that. But...
If you're preparing for a test tomorrow, it doesn't seem to me that we should be talking about this problem.
Yeah. This is part of their, this is actually...
Go ahead.
Oh yeah, this is part of the review for the test tomorrow.
Well, I don't know what to say. Maybe you had pre-calculus. In other words, maybe you had the calculus to solve this, and you weren't there that day, possibly?
I remember him doing one example problem of this and then never talking about it again.
But the only way to teach you how to solve this is with calculus, and
he briefly talked about it. Like it wasn't like
I can't cover that in 10 minutes. That is a 5-hour subject.
Yeah, he did it with the last 5 minutes of class. It's like,
well, that's crazy. Let's just go to the let's go to the next problem.
Okay.
This is also calculus, but this is calculus that you can understand.
Yeah.
a big part of calculus is determining where functions are increasing and where they are decreasing.
Okay.
So look at this graph. Starting from left to right, tell me where the function is increasing from.
It's increasing from -6, or let's see
Actually,
here,
it's negative.
0.
It's negative infinity. In other words,
Oh yeah.
if I
Infinity.
continue that arrow all the way, it not only goes down to negative infinity, but it also goes left to negative infinity.
Okay.
And when you're defining these intervals, you're
Mm-hmm.
always defining them according to the x-axis, not the y,
Okay.
the x.
Right.
So it's increasing from where I'm pointing, which is basically negative infinity,
Uh-huh.
to there, all the way to there. The x-coordinate of that is what?
-6.
No, it isn't.
Oh, which one are we looking at?
No, what I'm questioning is why the heck is he giving you functions that don't have integer values for their answers? Minus 6, it does not stop increasing there.
No.
It increases from negative infinity all
To the vertex of that.
Yeah, the x value of that, which looks to be about 4 1/3, negative 4 1/3.
Right.
Okay, that's the important number there. That's what it.
Uh-huh.
That's the interval it's increasing on.
Okay.
Then it starts decreasing, and it decreases from that point, whatever it is, all the way to this point, which
Right.
looks to be about 1. In other words, each of these grids is 2.
Yeah.
And so this point looks to be about 1. So
Yeah.
you would say it's increasing from negative infinity to negative, we'll call that -5.
Uh-huh. Yeah, I guess so. I mean,
Not only is this not a problem that he should be giving you, but he's put all of this information on it that is horrible. These
right.
zeros are completely irrelevant to whether it's increasing or decreasing.
Uh-huh.
Who's your teacher?
Mr. Alonzo.
Alonzo, okay.
Yeah.
Well, this is a crazy question to begin.
This is.
But even still, we can answer it. It's decreasing from -5 to +1.
Okay.
And then it's increasing from +1 to infinity.
Okay.
The 3 numbers that he has listed on here are indeed zeros of the function, where it crosses the x-axis, but that's not what determines increasing and decreasing.
Right.
You know what increasing is, right? You see why it's increasing from this point to that point?
Yeah. From negative infinity to -5.
Right, because then it turns around and it starts decreasing.
Right.
And there's a point there where if you drew the tangent line, it would have a flat slope.
Okay.
That's the whole point of calculus.
Yeah.
That when the slope of the tangent line is 0 or horizontal, you're going to find a place on the curve that is a local maximum. That's the maximum of the function over a certain range or a certain domain. And this will be the minimum. And notice that at the minimum, you also have a flat tangent line.
Yep.
That's the key to calculus.
Okay.
All right, let's look at 39. It makes a little more sense. Where are we increasing from?
From negative infinity to 1.
You know, I'm not sure that this necessarily goes to negative infinity on the x-axis. It almost looks like the y-axis is a vertical asymptote. And I don't know what this function is. They haven't given us the function. But I can't really tell. The arrow, I'm not sure that necessarily means it goes to negative infinity on both axes.
Right.
It might just go to negative infinity on the y-axis. which means it would be increasing from 0 to 1.
From 0 to 1.
I can't really tell unless there's some definition to this arrow that I'm not familiar with.
Yeah.
If that arrow means it goes to infinity in both directions, then your first answer was correct. But
Okay.
if I look at it, it almost looks, does it not look like asymptotic? In other words, it looks like a log function. If I draw a function, here's a log function.
Okay.
The domain on that is 0 to infinity. It's not negative 0. In other words, I don't know that if I put an arrow on it, if that matters or not, though.
I'm not sure.
But
Yeah.
I'm not either. So that's what would depend on that. What's happening? Where is it decreasing from?
I'll say from 3 to negative infinity if the line is infinite, like.
Well, okay, good. But it's also decreasing from 1 to 2.
It is, yeah.
And it's also increasing from 2 to 3.
Okay.
So wherever the function is going in one direction only, that's the interval that it's increasing or decreasing on.
Okay. Yeah.
Now number 40, they don't give us the graph, but they give us the calculus.
Okay.
You're into calculus. Like it or not, you're into calculus. There's no avoiding it.
No, there isn't.
Well, let me give you the simple answer that I can give you in 10 minutes.
Sure.
If I have a function, and it's equal to that, and I want to take the derivative of that function, I use what is called the power rule. I take the exponent, I put it in front, and I subtract 1 from it.
Okay.
Okay? Now, the relationship between a function and its first derivative is if a function is increasing, its first derivative will always be positive.
Okay. Well, how would you, I'm sorry, like how would you get from...
If a function is decreasing, first derivative will be negative. So if I took these functions that they drew, these two graphs, and I were to draw the first derivative graph, the only thing I know for sure is that the first derivative would be positive from there to there. It would be negative from that point to that point, and it would be positive from this point all the way.
Okay.
So that's the most important relationship you can remember in calculus. Calculus is all about manipulating functions.
Okay.
Okay? And first derivative is a manipulation of the original function. And it's pretty easy to do as long as the function is simple. But they're giving us nothing but simple functions here. So we can figure out first derivatives. Well, if this is true and I can apply it to each term, and in our case we have g of x is equal to x squared plus 5x plus 1.
Yeah.
Let's figure out what g prime of x is. Start with the exponent. Multiply, subtract 1 from the exponent, what do you get?
What you get?
Start with the exponent.
Okay. So it would be 2x.
That's it. 2x to the 1. 2x to the 1 power. You don't have to take 1.
Right.
In the second term, the exponent is 1, right?
Yeah.
We're going to take that 1, multiply it by the 5, we get 5, and when you subtract 1, you get x to the 0, which is always 1. So the derivative of 5x is 5.
Okay.
The derivative of any number is 0.
Right.
So this is our final answer for the first derivative.
Okay.
Now here's what's true.
Uh-huh.
When the first derivative is greater than 0, the function
Uh-huh.
g of x is increasing.
Okay.
When the first derivative is less than 0,
Yeah.
the original function is decreasing.
Okay. So for this one, if the let's see here. So if it was like an equation like x to the third plus
Now let's
4x plus
take this one right here, because this is the problem you have. Let's do the
okay.
problem that they gave you.
Sure.
Okay, so this is the first derivative.
Uh-huh.
So to figure out where the original function is increasing and decreasing, I need to solve this. And the way I solve it, let me work through one with you.
Sure.
The only way you're going to get it. If this
Right.
is all foreign to you, then I don't know if you're going to get it, because it's pretty complicated stuff.
Yeah.
So g prime of x is 2x plus 5.
Uh-huh.
And I want to know where that's greater than 0. Can you
Yeah.
solve that inequality?
You can.
Do it.
Yeah. You would subtract 5 from both sides, so it'd be 2x is greater than negative 5, yeah. And then you divide by 2x.
Divide by 2.
Or 2, my bad, so it'd be x is greater than minus 5 over 2.
So that tells you that everywhere to the right of minus 5 halves, the function
Uh-huh.
is increasing.
Yeah.
So that's the interval that it's increasing on. So the answer, the answer would be either x is greater than minus 5 halves, but if you wanted to put it in interval notation, it would be minus 5 halves, comma, infinity.
Okay.
Now let's figure out where the function, the original function, not the derivative function, the original function is decreasing. Well, that is where the derivative is less than 0. So solve this.
Okay. So we'd subtract 5 again. Hold on, let me write this down. Alright, so it'd be x is less than, minus 5 over 2. Or, yeah, minus 5 over 2.
And in interval notation, that's negative infinity to minus 5 halves.
Yeah.
So if I was attempting to draw the original function, and keep straight here, the derivative is not the same as the original function. The first derivative is the rate of change of the original function.
Okay.
Basically, that's the verbal definition of it.
Right.
But what I know is that if I go to minus 5 halves, the function is decreasing to that point, and then it's increasing anywhere greater than 5 halves. Well, that looks like a parabola, right?
It does, yeah.
If you take your original function, that's a quadratic, that is a parabola. And if we were to graph that in either your graphing calculator or on my Wolfram Alpha, I'm going to get something that looks like this. It might not look quite like that. It could look something like this. The red function is still decreasing from negative infinity to negative 5 halves, and it's still increasing from minus 5 halves to infinity, but doesn't matter whether it's the black function or the red function. The only thing they were asking was where is it increasing and where is it decreasing. And the black function and the red function are decreasing on the same interval and increasing on the same interval. So do you use interval notation, or is it acceptable to just say x has to be greater than minus 5 halves?
He hasn't really made that clear. I would think we could just leave it like that, like x is greater than or x is less than.
Interval notation is a little bit more specific, but a lot of teachers will be fine with this notation.
Yeah.
That's pretty specific also, if you think about it.
It is, yeah.
All right. Still don't know why you are getting these problems, but
Me neither, yeah.
hold on one second. Let me close my door.
Yeah, no problem.
All right, so here we have a cubic that they want you to sketch a graph of. All right, this one you should probably know how to do.
Yeah.
And the next one. So
yeah.
Let's talk about this.
Would you do synthetic division for this one?
No.
No.
You
Okay.
solve it by grouping.
Oh, okay.
There's a very, very small percentage of cubic equations that can be solved by grouping.
Okay.
And what you need for it to be solved by grouping is for the ratio of this, the coefficient of x cubed to x squared be the same as the ratio of the coefficient of x to the constant. Well, what's this coefficient? Minus 1/5, right?
Uh-huh.
What's this coefficient? Minus 4/20. That's also minus 1/5.
Okay.
Because they're the same, you can solve it using grouping.
That makes sense.
Well,
Okay.
I don't know how much sense it makes, but it's a hell of a lot easier than the other alternative for solving it, which is called the rational factor theorem and probably takes 30 minutes to do.
So if they're not the same, then you can't do factor by grouping?
If they are not exactly the same ratio, then you cannot use grouping to solve it. In other words, if I make that a 19, I'm dead meat. I got to do the extra hard way.
Gotcha. Okay.
All right. So how do we solve it by grouping? Well, basically, we're going to group the two terms on the left and the two terms on the right together.
Okay.
But you have to be extremely careful when in between there's a negative sign. If there's a positive sign, then I can just add parentheses and proceed. But if there's a negative sign, then not so easy. You'll see exactly what happens. Let me demonstrate. In other words, if I merely put parentheses around the two terms on the left and the two terms on the right, I do not get the same function.
No.
That second row is not the same as the first row.
No.
Distribute this negative sign and it turns into minus 4x minus 20.
Which isn't the same, yeah.
Not the same. And the key on all math, when you're manipulating functions and you're not trying to make them different, then you got to make sure you don't change it. And the only way that this does not get changed is if I make that a minus 20.
Okay.
Okay?
Yeah.
So you're clear that the first row is the same as the second row. In other words, if I remove the parentheses on the second row, I get what I started with.
Yeah. I did get that.
Factor out the greatest common factor between the first set of parentheses. The greatest
X
factor.
Just X.
No? X squared.
Yeah, X squared.
Can I not divide both terms by X squared and get an integer type answer? What is my answer when I divide both terms by X squared?
In the parentheses, it would just be X minus 5.
Good.
Cool.
Now over here, do the same thing. Take out the greatest common factor. What is it?
Okay. 2.
How about 4?
Would 4? Yeah, 4 would work.
4
yeah.
Very well. and
Uh-huh.
leaves x minus 5.
Yeah.
Okay? And
Cool.
as long as that binomial is the same as that binomial, then the next step is to factor out the binomial.
Okay.
So I'm going to factor out the x minus 5, and what's left over?
X minus,
X squared
yeah, so it'd be x squared minus 5, or well,
minus 4. Remember what you're doing when you're factoring. You're dividing each term.
okay.
When I say I'm going to factor out the x minus 5, this is what I'm doing. I'm going to divide that by x minus 5, and I'm going to divide that by x minus 5. Well, what do? You get x squared minus 4.
Okay.
Okay?
Oh.
So if I multiply those two things together,
Uh-huh.
I get this cubic.
Okay.
Okay? So I have factored it. Now, I can factor it a little bit further because that x squared minus 4 is difference of perfect squares, right?
Right. So you could take half of that and then square that.
How do you factor difference of perfect squares?
Well, you take half of the minus 4, right?
Not half, the square root.
Or the square root,
In
yeah.
other words, it's x minus 2 and x plus 2. It's
Okay.
half in this case, but it's rarely half. In other words, make that a 9, and now it's x minus 3 times x plus 3.
Uh-huh.
So what I'm really doing is taking the square root, not half.
Okay.
Okay?
Yeah.
But that's the way you factor difference of perfect squares. So this is now our function.
Okay.
Okay? They want us to graph it.
Yeah.
Well, where do I know it crosses the x-axis?
At minus 5, minus 2, and then plus 2.
No.
Uh,
That's a factor. That's not the 0. 0 is at plus 5.
so plus 5 and then plus 2, then minus 2.
Right.
Okay, cool.
In other words, your 0 is usually the opposite sign of your linear factor.
Yeah.
Okay? Now,
Okay.
I know the function either looks like this, because that's what cubics look like,
Uh-huh.
but it might also look like this. In other words, it might come from the top.
And go, yeah.
Yeah.
Go down.
Okay. So it's either the red or the black. I've identified the zeros by factoring the thing.
Yeah.
How can I figure out whether it's the left or whether it's the red or the black?
By the exponent.
By the end behavior.
Or by the end behavior.
Okay. If we go back to our original function,
Uh-huh.
the top one,
Yeah.
the end behavior is determined 100% by the highest degree polynomial.
Uh-huh.
So end behavior means what does p of x do when x goes to positive infinity, and what does p of x do when x goes to negative infinity? Well,
Okay.
let's take the positive infinity. What's positive infinity cubed?
Positive infinity.
Okay, so as x is the horizontal axis,
Uh-huh.
vertical axis, as x goes to positive infinity, p of x goes to positive infinity. That means it's the black line, not the red line.
Right.
Okay? Let's just check the other direction, just to make sure.
Yeah.
As x goes to negative infinity, what is negative infinity cubed?
Negative times a negative is positive times a negative, so negative.
Exactly. That is negative infinity. In other words, when x goes to negative infinity, p of x should be going to negative infinity also, is it?
No.
Yeah, it is. Sure it is. As x is going to the left as far as it can go, p of x is going down as far as it can go.
Okay.
So I've figured out it works on the right and it works on the left. I'm going to erase the red because that's not the function. The function is this black function. It goes through all three zeros, and it also has the correct end behavior.
Yeah.
Only point we didn't identify, I hate this program. The only point we didn't identify was the Y-intercept. What's that point right there?
Which point? Oh, the X right there. That one is 2, 0.
How do you figure out the Y-intercept?
You just plug in.
Plug in what?
You plug in the zeros with X.
Okay, what do you get when you do that with this function? If you plug in x equals 0.
You get -7.
X equals 0.
Oh, wait. Oh. So it'd be -5.
No. Anything multiplied by 0 is 0. So this term goes to 0, this term goes to 0, this term goes to 0.
Oh, right.
What's the Y-intercept? 20. It's the only thing that's left. In other words, if this term goes to 0, this term goes to 0, and this term goes to 0, when I plug in 0 for x, then p of x is 20. So this point is 0, 20.
Okay.
Where it crosses the Y-intercept. Now I have the Y-intercept, I have all three x-intercepts, and I have my end behavior correctly.
Okay.
That means I've got a near perfect graph of this function.
Yeah.
If I were to graph this function on Wolfram Alpha, it would look very, very close to this. And maybe my grid is off a little bit. In other words, if this is 2 units, I might have to put this Y-intercept a little higher up so that maybe it looks more like this.
Yeah.
But that's how I graph the cubic.
Okay.
Without a calculator. Is I have to factor it first. When I factor it all the way down, I see 3 different zeros. And I know the graph has to go through all 3 zeros.
Okay.
All right, let's look at 42. We'll have just about enough time to finish it.
Yeah.
Here, h of x equals this. And so finding the zeros is very important. So you find the zeros by factoring. What can I do here?
You can find greatest common factor.
What is it?
X squared.
Good. What's left over?
So it would be x squared plus x minus 6x.
Minus what?
By
x squared. What do you get?
minus 6. Oh, yeah, minus 6, yeah.
Sometimes I feel like you say not what you're thinking. I kind of feel like your brain was thinking minus 6 and it came out minus 6x squared.
Did I say that?
Minus 6x. Yeah, you definitely had an x.
Oh. Yeah, I think I did.
I don't really feel like you were thinking that. I think you were thinking minus 6.
I was thinking minus 6.
So,
Yeah, I just came out minus 6x by mistake.
well, that's actually an advantage of online tutoring, is it forces you to match up what you're saying with what you're writing.
Yeah, for
If
sure.
you do all of this on your own, let's say you did all this homework on yourself, you would write down minus 6 and you'd never catch that, the fact that you're saying something else.
Right.
So it's actually good for you
That's good.
to have to verbalize this.
Uh-huh.
Factor
For sure.
x squared plus x minus 6, because that's factorable.
Um, it would be, well, wouldn't that be x cubed then? Like in the parentheses?
No, we're unmultiplying it. In
Oh,
other words, we're factoring it. When you factor something, you basically are splitting it into its linear factors.
okay.
Okay, so what are they? You have to know how to factor. You can't go anywhere in math without knowing how to factor.
Yeah, it'd be x minus 3 and then x plus 2.
Well, now check the middle term there.
The middle term minus 3x.
No, the middle term is made up of the inside multiplied together and the outside multiplied together, and add them
Uh-huh.
together. You get minus x. Is that your middle term?
No.
That's not right then.
Uh-uh. So it'd have to be x plus 3 and then x minus 2.
There you go. Hold on. This might be
Okay.
the worst drawing program I've ever seen.
No worries.
No, it is. Because if you happen to be in erase mode and you touch anywhere, it takes out half of what you didn't really want taken out. Okay?
Ah, jeez.
So,
Yeah.
all right. So this is our function. Do we
Uh-huh.
know our zeros?
Yeah, minus 3 and then plus 2.
Well, what about this one?
Um,
In other words, your zeros come from setting each of your linear factors to 0.
yeah.
So I got to set that to 0 also. So I actually have 3 zeros. I have x equals 0 with multiplicity of 2. I have x equal minus 3 with single multiplicity. And I have x equal 2 with single multiplicity. Now, do you know what I mean by that term?
Kind of. I kind of have an
In
idea.
other words, what x
Oh,
squared actually is x times x.
right.
So really there were 2 zeros.
Okay.
In other words, we started with a quartic. So we expect
Uh-huh.
4 solutions. It's just that 2
Okay.
of the solutions are the same. In other
Uh-huh.
words, I'm going to let this equal to 0. I'm going to let this equal to 0. I'm going to let that equal to 0. And I'm going to let that equal to 0. If I've
Okay.
got 4 things multiplied together equaling 0, then that's how I solve it, is I let each of the 4 equal 0. So when I say one of the solutions is 0 with multiplicity of 2, that's what it means.
Okay.
Okay?
Yeah.
Now, that has implications for how the curve looks. Fairly significant ones. And
Okay.
here's what happens. I'm going to put an X through my zeros.
Okay.
I know the curve has to go through these points.
Yeah.
Or not necessarily through them, but touching them.
Uh-huh.
When you have an even multiplicity, it touches the curve. It doesn't go through them. It's either
Yeah.
do something like this, or if it's coming from the bottom, it's going to do that.
Uh-huh.
At the 0 that we're x is equal to 0, the curve's going to look like one of these two. I'll figure that out later, but just telling you that when you have a multiplicity that is even, not odd, 2 is even,
Uh-huh.
and you don't go through the curve. You don't go through the x-axis. Okay?
Okay.
So here's
Yeah.
what my curve's going to look like. Either one of these two cases. I'm going to go through that because that has single multiplicity.
Uh-huh.
I'm going to kiss that only and come back up. And then I got to go through that because that only has single multiplicity.
Yeah.
So that's one possible curve. Another possible curve would look the other way.
Uh-huh.
Come back, kiss that, go away from it, come back, go through that curve.
Okay.
Again, it's one of these two curves. Once you find the zeros, it all depends on the end behavior as to whether it's the red or the black curve.
Yeah.
Well, let's examine end behavior.
All right.
Going back to the original function, well, let's look at this function over here on the left. That's the easiest way to look at it.
Uh-huh.
End behavior is only predicated on which term?
The leading coefficient.
X to the fourth, not the leading coefficient, but the leading,
Just
the highest degree
exponent.
exponent.
Okay.
So I don't care about the x to the third. I don't care about the minus 6x squared. I care only what happens to x to the fourth. What happens to x to the fourth as x goes to positive infinity?
It goes. It goes. Well, it is positive infinity.
Ah, that would indicate the red, right?
Yeah.
Because as we're going to positive infinity in that direction, we're going up to positive infinity in the h of x direction.
Uh-huh.
So it's the red, not the black.
So, yeah.
Let's make sure the left side works.
Okay.
What happens as x goes to negative infinity?
As x goes to negative infinity.
What's negative infinity to the fourth power?
Positive infinity.
Yeah. That's
Yeah.
exactly what our curve does.
Yeah.
That's what our red curve does. Our black curve doesn't do that. So
Okay.
we've definitely proven that it's not the black curve, but it's the red curve. And we were able to graph it merely by factoring it and knowing about multiplicity and what that causes graphs to look like.
Yeah.
This is pretty advanced stuff that you and I have never ever done before. So I'm a little shocked. The only thing we've ever done that's close is factoring a cubic by grouping. But we've never talked about multiplicity. We've never talked about increasing and decreasing functions. And we've certainly never done a problem, the open box problem, which requires also calculus.
Yeah. This is pretty advanced.
As long as we have 7 minutes, look at that calculus problem.
Sure.
Because we did some calculus already. So here's what we had. Man.
Yeah, I have it written down. It was 18 minus 2x, 13 minus 2x, and then just x.
So the volume as a function of x was 18 minus 2x, which was the base.
Yep.
The width was 13 minus 2x, and the height was just x.
Yeah.
Okay, what we want to do is multiply that out. So the first thing I'm going to do is multiply the binomials. Do you have a calculator? What's 18 times 13?
I do.
That's 234. Never mind. I know how to do it.
Okay. I could pull it out if you need it.
Yeah, I don't think I need it. I just realized how you do that. That's 180 plus 54. So that's 234. Okay, and then we got minus 36x minus 26x. That's minus 52x.
Yep.
Then I got minus 2 times minus 2x times minus 2x is plus 4x squared. That's all in parentheses, all being multiplied by x.
Yep.
Let's put it in order of the highest degree polynomial first.
Yeah.
So that's our volume
Uh-huh.
as a function of x. Now, we already know what cubics tend to look like, right?
Uh-huh.
In other words, cubics tend to look like this.
Right.
We want the maximum volume.
Okay.
Well, that comes right there.
Uh-huh.
Because this point over here is when x is a number outside our domain. In other words, remember that it doesn't make any sense for x to be 0. It doesn't make any sense for x to be greater than 13 or half of 13. In other words, if I made x 6.5, I wouldn't have a box. I would have a folded up briefcase that had no volume at all.
Yeah.
So x has to be between 0 and 6.5. So let's put 6.5 right there. Okay.
Uh-huh.
So this value right there, remember that's volume.
Yeah.
I want to find the x that corresponds to that peak of that curve.
Okay.
It's a calculus problem. I take the first derivative of the function. Remember, I just used that power rule. I start with the exponent, multiply it by 4. That gives you 12. Subtract 1 from the exponent. Go to the next term. Multiply 2 times 52. 104x plus 234.
Yeah.
That's the first derivative. What the first derivative means is what is the slope of the tangent line? Well, I'm looking for the tangent line to have a slope of 0.
Uh-huh.
I don't want the tangent line that does this. I don't want the tangent line that does that. I want the tangent line that shows me that peak. And
Okay.
that tangent line has a slope of 0. And when I take the first derivative of a function, what I'm getting is the slope of the tangent line. That is the definition of it.
All right.
So I solve this now by setting it all equal to 0. In other words, v prime of x is the slope of the tangent line. I want to make the tangent line slope 0. That's going to find this peak for me. Well, we frequently have quadratics equal to 0. Factor that, and you'll actually get two answers. You get this answer here, but you also get this answer over there, which is kind of a minimum value.
Yeah.
But it also has a tangent line whose slope is 0. So you take the one that gives you the highest volume.
Uh-huh.
And that's this one here. And whatever your calculator, if you use your calculator to factor that, whatever x value, that's what they're looking for. So how do you make the cuts? Well, you make the cuts by figuring out what x is going to be. And like I said, x does not end up being a whole number here. It ends up being a very odd number that you would never figure out without calculus.
Uh-huh.
Okay? And then as far as what the volume is, go to your original volume function right there.
Uh-huh.
Plug in the value of x that you solved for.
Okay.
That'll actually give you the actual volume of the box.
Okay.
Then you take that volume, let's say you end up with 100 cubic inches of volume, and you divide it by how much each M&M takes up, which is this.
Uh-huh.
So you take whatever volume you got, you divide it by how much volume each M&M takes up, and that gives you how many M&Ms you can put in that box.
Okay.
And I don't have any idea what that number is going to be because I don't know what the volume would be without going through all the math. But I still can't believe they gave you this problem.
Jeez. Gosh.
And
And not only like is it calculus, it just takes a while too. So if he has like
calculus is hard. There's nothing easy about calculus.
no, not at
Calculus
all.
is terrifically hard. There's just no way you'd have any chance of doing this problem unless you'd gone over it in class. But
Uh-huh.
like I said, maybe you missed that day or something.
Maybe.
I can't teach you calculus in an hour session.
No.
I taught somebody calculus this summer over 4 hours, and I gave him a pretty good fundamental basic calculus course so that when he actually took calculus this semester, he had a chance.
Uh-huh. Good.
Not a great chance, but a chance.
But a chance, yeah.
Passing it, yeah.
Uh-huh.
Only with the preliminary work that we did in the summer is he doing okay, and I think he's getting a C.
Wow.
But
Okay.
calculus is tough. Tough.
It really is. Yeah. But,
Even
okay.
if you had a little bit of calculus, you should not be getting this problem. This problem requires you to make derivatives and find slope of tangent lines and extrema and all kinds of stuff. This is like the calculus you would be getting maybe in the third or fourth or fifth week of a calculus class.
Wow.
What the hell
Okay.
are you getting it for in the
I
end of your first semester?
Uh-huh.
Mr. What is his name?
Mr. Alonzo.
Alonzo?
Yeah.
All right.
Uh-huh.
He's going on my list.
Cool. Yeah.
Just kidding, but not really.
No, I know. Yeah, I know exactly what you mean. Just,
All right, Dylan.
all right.
You have an appointment tomorrow night also, or no?
I don't
no,
think
you're
so. We have the test
you're
tomorrow.
testing
Yeah.
tomorrow, so we moved your appointment to tonight. Okay.
Yeah. Yep.
Thank you.
Cool.
I am done. You have a good evening and good luck on your test. I hope you don't have too many calculus questions.
Hopefully not. Yeah, and I feel like I know the concept pretty well. There's a stat page that I was a little hesitant on, so
Yeah, complicated stuff. I
for sure.
wouldn't expect you to really understand it. You don't.
Yeah.
You don't learn calculus in an hour. You just don't.
No, it just doesn't happen like that.
No,
It doesn't
nobody
work
does.
like that.
Not just you, but nobody does.
Right.
I'm
Yep.
not sure how many people learn it in 10 hours.
Oh, I'm not sure either. Yeah.
So this makes no sense at all. It's almost like you got somebody else's review material.
Right. Yeah, it does feel like that, honestly.
All right, Dylan.
Awesome.
Talk to you
Alrighty.
later.
Sounds good. Thank you, Mr. Cowan.
Bye-bye.